Here we go. Today is Wednesday, February the 1st. Can you believe that it's February the 1st? We are February, March, April. May the 1st, we take the AP test. 3 months away. We're finished with kinetics. 2 weeks on equilibrium. 2 weeks on electrochemistry. 4 weeks on acids and bases. We are done. Okay? All right. We have those units left. That's it. Okay? We will be finished with our curriculum, hopefully, because we do have spring break in there in March, but I think it's the last week in March, so we may have to come back and only have 3 weeks, or we might come back and use 1 week in April. We'll see. Hopefully we'll be done before spring break with all of acids and bases, and then we can use the entire month of April to review. And then we take the test, and everybody makes a 5 on May the 1st. Then we play ping pong from then on out. Okay? So I love it when we can kind of summarize the rest of the semester just that quickly, that easily. That means we're getting very close. Okay? So the reality is we did the lion's share of all the work first semester. Okay? Now, what we're doing here, these are the big concepts of the kinetics and equilibrium and redox reactions and all that. But once you have all of the foundational chemistry, these things just kind of fall into place because we're just having to then to isolate. So we began talking yesterday about equilibrium. The state we're in a reversible reaction. The key is that the rate of the forward reaction equals the rate of the reverse reaction. Okay? Equilibrium doesn't mean that the concentrations are equal. Simply means that the rate of the forward reaction and the rate of the reverse reaction are equal. Okay? So, in doing that then, we have this equilibrium constant expression, or the law of mass action. Now, I just kind of wrote it just a little bit differently today than what I had it yesterday. But it says that it's the ratio of the products over the reactants raised to powers, and your x and y are the coefficients from the balanced equation. Now, what do we exclude from the expression? What states? Okay? So we can say here that solids and liquids are excluded from the expression. Okay? So solids and liquids are excluded. And the reason for that is they say that the concentration of those solids and liquids aren't going to change that much. They're pretty much going to be constant. So since they're constant times a constant, that's figured into the constant. Okay? Just before we really get going here, can we maybe open that window? I feel like I'm already sweating. We're already a sphere down. Okay? That makes it hot in here. All right. So we have 2 different ways in which we can express our equilibrium constant. KEQ is just the general equilibrium constant. So we put the little subscript, oh, that feels so good. The equilibrium EQ just to kind of say, okay, this is my equilibrium constant, so I know it's capital K. But there are 2 ways we can express the, quote, concentrations, either in terms of, if it's aqueous substances, we put it in terms of molarity, but if it's an all gas, we can either do molarity or we can do it in terms of pressure, and then it would be Kp. Kc and Kp, obviously they're expressed in different units, so they're not going to equal one another. However, you can equate them together with a simple equation. Okay? We no longer have to do that equation, so we're not even going to talk about it. And then yesterday, we ended the day kind of talking about Le Chatelier's principle. And Le Chatelier's principle says, when a stress is applied to a system at equilibrium, the equilibrium shifts in such a way as to relieve the stress. I'm looking for there it is, for my teeter-totter, my meter stick. Okay? So when we're looking at this, equilibrium means we're balanced. The forward rate and the reverse rate are equal, so everything's going to stay, the concentrations are staying balanced. But then we put a stress on it. And we have our stresses here. We change the concentration. So if I add some reactant, what's that going to do to the rate of the reaction going this way? If I add more reactants, again, we use the example hydrogen plus oxygen goes to H2O. If I increase the amount of hydrogen, it's going to go faster that way. It's going to want to use up that hydrogen. But in terms of kinetics, Why does that happen? Because more concentration means more collisions, which means probability of where. Okay? What we heard as a mumble jumble is we heard that it increases the concentration, which increases the number of collisions, which increases the probability of having the proper orientation where reactant bonds begin to break and product bonds begin to form. Okay? That's the one thing that you'll remember when you're my age from AP chemistry. Something about product bonds breaking, forming or something. I don't know. It was something like that. Okay? So, changing the concentration, it's always going to move away from whatever you add to try to use it up. Now again, it's only if you change something that's in the equilibrium expression. So if you add a solid or a liquid, it's not going to have any effect. Changing the temperature. We have to look at our thermochemistry. We have to look at where is temperature. Is it endothermic or is it exothermic? And so is heat going to be on the left? Is heat going to be on the right? Increasing the temperature is the equivalent of adding heat, so it's always going to move in the endothermic direction. So if heat's over here, it's going to move this way. If it's an exothermic and heat's over here, it's going to come back this way. And the same thing, then obviously we do the vice versa on that, to where then if we remove heat, then it's going to go back towards to try and replace the heat. Okay? And then we talked about changing the container volume. So if we have gases and all of a sudden we cram them down into a smaller space, well now they're going to go and try and go to the side with fewer moles of gas. If you expand it, you're going to try and fill the space, or you're going to want to go to the side with more moles of gas. And we did practice problems in the book with those. And then what does the catalyst do? Get you to equilibrium faster, okay? It doesn't do anything with the thermochemistry, doesn't change the energy of the reactants or the products or delta H, and it doesn't do anything in terms of your equilibrium constant K. What's the only thing that's going to change the value of our equilibrium constant K? Temperature. So changing the concentrations makes the reaction shift left and right and all that, but the ratio of products to reactants raised to powers is always going to be the same. The only thing that's going to change this number is temperature. All right? And then there's the last one, number 5, that I didn't have space for, is what happens if I have an all gas and I add in like a noble gas? No effect, because it doesn't change the partial pressure of the gases at all. Remember, gases all act independently, so even though the total pressure increases, the partial pressure of the individual gases, basically the concentration of the individual gases, stays the same. So it has no effect. So these are great multiple choice type questions. Giving you, okay, so here's the system at equilibrium, the temperature's increased, what's going to happen to the moles of reactant, the moles of products, how is it going to change? Just like we went all the way through on those practice problems in the book. Okay? Now, for the sake of the other class, which we did not get to go through all of those, let's do one more practice problem of Le Chatelier's principle and just kind of see how will that affect. How do these changes in concentration, changes in temperature affect the position of the equilibrium? So if you turn in the white book to the back of chapter 15, which is page 663, you turn right to it? Page 663. So first off, if I'm looking at this reaction right here, and I want to write the equilibrium expression, okay? Since it's given this, what is K going to equal? Kc is going to equal what? product. So what do I write? The concentration of O2 raised to 6th power times the concentration of the glucose. Why not? It's a solid, so we just ignored it, and it's just totally discriminated against because it's a solid. Okay? Products over reactants, so I'm going to put CO2 to the 6th as well. Okay? Now, if I want to do it in terms of Kp, what's Kp going to equal? So we say the pressure of the O2 to the 6th divided by the pressure of the CO2 also to the 6th. Okay? So if the question were to ask, just write the equilibrium expression for this reaction. That's what you would write. And then they might say in terms of Kc or Kp. That's all you write. Okay? So, I'm not going to have enough time. I got to get some memory on here. So, hey, 5th period. Actually, it's going to be 6th period tomorrow. There's going to be 2 files. So, when this runs out, look for the second one. All right. So now we want to look at Le Chatelier's principle. So how is the equilibrium yield of this going to change? So even though it's not in the equilibrium expression, if it shifts right, this will go up. If it shifts left, this is going to go down. Okay? But it's not going, adding more of this or adding more of that is not going to affect the position of the equilibrium. However, it will still increase or decrease. So increasing the pressure of the CO2, which way is it going to do? It's going to shift right, but the question is saying what's going to happen to the yield of this? It's going to increase. The reaction is going to shift right because we're going to have more CO2, which is going to cause the rate of the forward reaction to increase. So this is going to increase. Now eventually equilibrium will get reestablished, but just at the higher yield. Okay? Increasing the temperature. How do we know which way it's going to go? Delta H is positive, so where's it going to be in the equation? On the left, so increasing the temperature is going to make it go to the right. So what's going to happen to my glucose concentration? It's going to increase. All right? So obviously you have to know where, if it's endothermic or exothermic, so somewhere in the question they have to tell you that. Okay? So we know that this sign's positive, so it's endothermic, or it could be written here. If it was negative, it'd be on the right-hand side. All right? So removing some CO2. So now we have CO2. We remove some, so what's the reaction have to do? Shift back left to replace it. Okay? So what's going to happen to this concentration? It's going to decrease. I'm telling you, it doesn't get any harder than that for Le Chatelier's principle. So removing part of if we remove this, what's that going to do? Is it in this? So what effects are it going to have? None. Because you have solid sitting on the bottom, you're still going to have solid sitting on the bottom. It's not going to have any effect. If it's not in the equilibrium expression, changing the concentration of it's not going to have any effect. Okay? And then adding a catalyst, no effect, because it's just going to get to equilibrium faster. So we good with that? What if I added in some helium? Again, no effect, because it's not going to change the pressures of my two gases, because whether there's helium there or not, they're going to have the same partial pressures. Guys, you had a question? Oh, no. D? Okay, decreasing, you know why you don't know? Because we didn't talk about it. Decreasing the total pressure. Okay? Now, that one's kind of ambiguous, to be honest with you. Are they decreasing the pressure by removing each equal amounts of these? Are they decreasing the pressure by making the container bigger? But let's just say that they're decreasing the pressure by making the container bigger. What's that going to do?
It's not going to do anything because it's the same number.
That's right. It's not going to have any effect because since the coefficients are the same, it's not going to favor either side. So it would have no effect. Does anybody have any questions on that? Pretty straightforward, huh?
So let's say like on the products, instead of a 6 as a coefficient, it was an 8.
Yeah, if there's an 8, then decreasing the total pressure, let's say by increasing the container volume. If this is an 8 and this is a 6, what's it going to want to do? Okay, if you make it bigger, you want more moles of gas to be able to fill the volume. So it shifts to the right. If you decrease the volume, it's going to shift to the left because now they're all crammed. They want to make the fewer moles of gas, not the more moles of gas. Okay, good question. All right, so let's kind of look at a real life example. I'm over here. Move. Come on. Why am I not green? Oh, how does this battery go dead? Okay, a manual feed from here on too. All right, so if I take, let's measure out some quantities here. Because it doesn't upload as easily. I have to upload it to the Swivl account, and then it goes straight to YouTube. It's super easy. Oh, that's a good question. Can I make it? Oh, sorry, dog. I wonder if blinking, does that mean it's dead? It's still got something in it. Okay. It's a good question. Am I recording? And the other one doesn't work. How do I use the iPad microphone? Just unplug this?
Yeah.
Okay. Audio cable is not plugged in. I know, but can you hear me now? I don't know.
I want to check that before you start doing this.
Well, I had to stop it to check it.
Well, then upload 3 files.